I'm just going to do a short introduction and then we'll just hand it over to Riley. So I'm Riley's PhD thesis advisor. He has been here at the university for 5 years and in my group for just over 4 years. In that time, he has written 2 fully published peer-reviewed papers. A third one is nearly complete with just some edits with co-authors back and forth and is about to be submitted within probably a few days to a week of this defense. He also during that time has done quite a bit with science policy, a thing that he's very passionate about and has been doing alongside of his science PhD work. He has been interviewed numerous times on the media and for different publications, magazines. We were on Iowa Public Radio together, and he received a top downloaded paper award from Wiley Journals for his diffuse auroral eraser paper. So I think that kind of sums up Riley's career pretty well, but I'll let you take it away from here. And thanks everyone for coming.
Last piece, in terms of your career, where you have a job, is that? Oh yeah, we hear about that.
I guess I can start just with that. So yes, I have accepted a position at the Space Dynamics Laboratory, which is sort of, I call like a nonprofit scientific contractor for the Air Force out in Albuquerque. So I'll be moving down there at the beginning of August to start working on for atmospheric research and actually stuff that's fairly relevant to the stuff we'll go over today.
Cool, thank you.
We'll start, thanks for all coming in this early morning. Getting out of bed and coming here. I'm really honored to be able to tell you about the work I've been doing over the past 4.5 years here at the University of Iowa, looking at this specific type of aurora that we call diffuse-like and dynamic aurora. But before we begin, I do want to extend a huge thanks to my advisor, Allison James. I know the last 4.5, 5 years haven't been necessarily the easiest, being one of the first grad students in the group and going through COVID. There was this rocket launch that got delayed several years. But throughout it all, she was always there, very supportive, helping me to support me. Any questions I had, she was there to answer them, to give advice. And I think she's really, in part, one of the reasons I've been able to make it through to this point here. And so I'm really grateful for that, and thank you. So I just want to give a quick overview of what we're going to talk about today. So expect this presentation to take about 45 minutes, and it'll kind of be split into 4 different sections. First, which will take about half of the presentation, we're going to go over just some general background information about the aurora, what causes them, where they come from, the impacts they have on the atmosphere, just to get us all to the same page when we start talking about the actual research I've done. So after talking the kind of introduction, we'll go into the specifics of some of the research I've done concerning pulsating aurora, which is a specific type of this diffuse-like and dynamic aurora. We'll start with looking at the energy of this aurora and the impacts it can have on the atmosphere. And after looking at that, we're actually going to follow up on a sort of interesting lead from that research that we use to better understand where this pulsating aurora actually originates from, how it forms. And then finally, we'll finish off on this diffuse auroral eraser that Allison mentioned briefly, which is a type of this diffuse-like and dynamic aurora that's similar to pulsating aurora, but also intriguingly different. So if we start here, so if you're anything like me, when you think about the aurora, you think about these really bright green arcs and curtains of vibrant light that'll occur in the northern or southern high latitudes. Sort of like this picture here. So this is one, I think my mom is on the Zoom call, that she took a few weeks ago in one of the largest sort of auroral storm events that has happened in the last decade. In fact, this particular storm was so strong that there were actually some sightings down here in Iowa. This picture here on the left was one that was taken from just north of Cedar Rapids. Though everyone here saw, everyone I talked to when they tried to look out here in Iowa City, it was just cloudy, so of course we weren't able to see it. So in the scientific community, we call this type of aurora, this bright, vibrant stuff, we call it discrete or substorm aurora. And it's extremely photogenic. It's what a lot of the images you're going to see are of, but it's also not the only type of aurora that's out there. Pulsating aurora, as this video shows here, looks like these blobs and patches, a much more dim, diffuse aurora that will blink on and off in a variety of sizes, shapes, and periods. Now, this pulsating aurora is actually very common. And when it does occur, as you can kind of see in this video, it'll often expand over a very large portion of the sky, and it can even last for hours at a time. The pictures here on the left just show what this pulsating aurora would look like in black and white from an imager that's known as an all-sky imager. So it has the ability to capture the entire 180-degree field view of the night sky. And this sequence of images over approximately 20 seconds, you can see this pulsating aurora is off in the top, and it turns on again in this middle one, and then off again in the bottom. So that's what pulsating aurora looks like in these all-sky imagers. In fact, all-sky imagers are really important for auroral research, and are one of the main ways we look at and study the aurora, because we can design them to run every night, all night, and really start to understand the dynamics of the aurora and how it changes over the course of a night, and understand what maybe a typical active auroral night would look like. And so if you were actually standing under the aurora, say in Fairbanks, Alaska, somewhere where you might see them, on a typical really active night, you might start by see a band of discrete aurora stretching from east to west in the northern sky. And that band would slowly start to move further and further south across the sky, until at some point it would reach so far south that it would stop, it would brighten and expand in this dramatic display across the sky, what we call an auroral substorm right there. And that auroral substorm would be bright and brilliant for 15, 20 minutes or so, and then it would slowly start to fade, and the aurora would become dimmer, diffuse, and you actually start to get then these patches that will start turning on and off in what we consider as pulsating aurora start happening there. And here actually you see a little brief flash there. This was actually the all-sky imager data from the night that we launched that rocket. Though I do want to mention that, well, that rocket did study pulsating aurora, and we were involved with it. That data is still being analyzed, so it's not part of this thesis itself. So looking at images like this, we can really start to understand that the aurora is this very dynamic, changing thing across the night. So one thing we might question then is there something else we could measure that would vary correspondingly to the aurora? It turns out, yes, there is. That thing is Earth's magnetic field. So if you put a magnetometer down on the ground where you're seeing the aurora, that's capable of measuring Earth's magnetic field, you might get a signature that looks a little something like this. So on the x-axis, you have time over the course of several hours here. And the y-axis is just a measure of the strength of Earth's magnetic field. And the different lines correspond to different directions in that field. Now, this data here is actually taken from that previous video I just showed you. And you'll notice right here at just after, or just around 10:30, you see this rapid and sudden, like the field, the lines here go kind of crazy on the graph, and they start going all over the place, much more active time. That actually corresponds directly to that rapid brightening and expansion of the aurora we saw in the previous video. And so we call this a magnetic substorm, corresponding to that auroral substorm. And this idea of a substorm is central to the dynamics of the aurora, and something that will pop up throughout this presentation, because it's also very important to pulsating aurora. As we saw in the video, you often have this pulsating aurora that will develop after one of these substorms. Now, the reason that the magnetic field, or the reason to understand why the magnetic field is actually important for how the aurora evolves, we have to understand what actually causes the aurora. So when we see the aurora, we're seeing photons that are produced in collisions in the upper atmosphere between these atmospheric molecules and electrons that are streaming in, precipitating in from outside of Earth's atmosphere through the top of the atmosphere down into it. And they collide with the molecules, and in that collision produce the light we see. Now, it actually turns out that the color of the light that we see corresponds to different heights in the atmosphere. So the most common color, being green, typically occurs between 100 to 120 kilometers. Sometimes you'll get these very deep reds that will occur at higher altitudes, upwards of 200 kilometers or higher. And then you can sometimes even get blues or violets that occur at lower altitudes. Now, because these electrons are coming in from outside of the atmosphere, coming down through it, a more energetic electron is moving faster and therefore can penetrate further into the atmosphere. And so you can actually sort of think of these colors almost as a proxy for energy. So the more energetic, the faster moving electrons will reach further into the atmosphere, and so they produce a slightly different color of the aurora. And the reason this has to do with the magnetic field is that, see, the aurora are caused by electrons. Electrons are charged particles, and charged particles can be controlled by magnetic fields. Now, if we look at the magnetic field of the Earth, close to the Earth, it looks something like the magnetic field of a bar magnet here, where the black lines here are the lines of magnetic field force, and we would call this orientation a dipole magnetic. So close to the Earth, it looks like a dipole. Now, if you notice, the bar magnet here is twisted a little bit. So that's not because I was being lazy when I was editing this, but it's actually because the internal sort of approximate bar magnet inside of Earth is actually slightly skewed away from Earth's rotational axis. And what this does is actually cause the magnetic north and south poles to be slightly different from the geographic north and south poles. I wanted to mention this just because if you hear me throughout this talk mention something like magnetic local time or magnetic latitude, just know that's basically the same as just a local time or latitude, except now we're measuring that based off of Earth's magnetic north pole, magnetic south pole instead of the geographic poles. Now, this still isn't the whole picture in regards to Earth's magnetic field. If we zoom out even further, we realize that Earth's magnetic field lives in this wider solar system. And in the solar system, obviously we have our sun. The sun is constantly spewing out this spray of charged particles that we call the solar wind. Within that solar wind, we have this embedded additional magnetic field. That solar wind spreads across the solar system until it eventually encounters Earth's magnetic field. And when it hits Earth's magnetic field, what happens is you get this compression and squashing of Earth's magnetic field on the side closest to the sun, and it ends up getting pulled and stretched away further from the sun. So in this picture here, the red lines correspond to those magnetic field lines. As from this configuration of Earth's magnetic field, we can start to point out where the electrons that cause the aurora come from. Now, we're not going to talk about it anymore in this talk, but I do want to mention that the discrete substorm aurora electrons, those tend to occur farther out here in this, we call the tail region behind the Earth. We're not going to talk about that more in this talk, but I just wanted to mention it. What we're really interested in is this region I've highlighted here, the green, the radiation belt region, because that's actually this region of very highly energetic electrons within Earth's magnetic field, and that is where pulsating aurora electrons come from. Now, if you squint closely at this, you can kind of see that that's the region of Earth's magnetic field that looks closest like a dipole. It's actually this dipole dynamic that causes these radiation belts that I mentioned. And to understand how those cause or form, we need to look a little bit at some dynamics and how electrons behave in a dipole field like this. So there are three sort of key motions that we need to look at. The first is right here on the left and the right figure. It's the gyro motion. So an electron in a magnetic field will have a tendency to spiral or circle around that magnetic field. If you then give it a little push in one direction, it will start spiraling around the field line like you see in this figure here. It spirals around this the magnetic field on the right. Now that's a very quick motion, and one rotation occurs on the order of 1/10,000th of a second for the rotation. Now, what you'll notice if you kind of look at the dipole here, if you imagine this electron spiraling around these magnetic field lines, spiraling around the magnetic field and moving along the field line. So as it moves along, it'll get closer and closer to one of these poles. Now, what you notice as you get closer and closer to the poles, these field lines are closer and closer together, which means that the magnetic field strength there is actually stronger. The effect this has on the particle is that its motion along the field line, and thus closer to the pole, starts to slow as the field gets stronger. At some point, it reaches a point where that speed actually goes to zero and it stops, and we call this the mirror point. So we'll spiral along here, get to this mirror point, stop, and then it will actually start moving in the opposite direction. And it will continue along the field line, again, spiraling until it reaches a similar mirror point at the opposite pole. And this is sort of, if you spread it out, you can kind of see this motion here. And what that'll actually cause the particle to do is bounce in between these two mirror points at the north and south pole and bounce back and forth, and basically in this what we call a magnetic trap. Now the final motion, and I guess I should say that bouncing basically between one pole back to that same pole takes about a second or so. So again, a pretty quick time scale. Now, the final motion here comes just due to the gradient you have in this magnetic field getting weaker as you go away, as well as the curve in the field. Specifics on that don't matter too much for this, but the effect is that as these particles are bouncing back and forth between poles, they actually have, the effect is that those particles then slowly will drift eastward around the planet, sort of tracing out this shape that you have here on the far right. And for a typical pulsating aurora electron, that drift around the planet will take on the order of 3 hours or so. And you combine all three of these motions together, you get what we call the Van Allen radiation belt. So in Earth's magnetic field, as these electrons are spiraling around the field line, bouncing back and forth between poles and drifting around, they trace out these sort of shell ring-like shapes around the planet that we see here in blue and red on the right. Now, there are actually two radiation belts. There's an inner in red and an outer here in blue. We're not going to look at the inner anymore. It's really the outer that those pulsating aurora electrons are coming from. Now, you might wonder, because I mentioned that these electrons are trapped in this magnetic field. So if they're trapped, how do they actually cause the aurora? How do they get into the atmosphere? So if you come back to this concept of this mirror point, where the particle at some point stops, turns around, and moves in the opposite direction, you can imagine if there is some sort of process that would cause the mirror point of that electron to occur close enough to the Earth that it would enter the atmosphere, then before that particle could reach that mirror point, it might collide with an atmospheric molecule and produce the aurora, which is actually the process that does cause pulsating aurora. And we'll talk about things that can actually cause that mirror point to change in a little bit. So because the electrons are coming from this region of the radiation belts, which is very energetic, it's got these very fast-moving electrons. When they actually enter the atmosphere, they can have very large impacts on the atmosphere itself. There are a variety of these, but one that's gotten a lot of research recently is that pulsating aurora can actually reduce ozone in the atmosphere. So this figure comes from a study, Veronin et al., 2021. And so the process that actually reduces ozone is that during these collisions with these pulsating aurora electrons in the atmosphere, you get these Knox and Hawkes particles that are produced. And this just shows in this particular instance, this increase in these particles. Now, these molecules actually have the ability to react with ozone and deplete it from the atmosphere. So the figure on the right shows the resultant decrease in ozone from this increase in these Knox and Hawkes particles during a period of pulsating aurora. And this particular study found that in certain cases of pulsating aurora, you can actually reduce the ozone by nearly 10% in certain regions. Now, I'm not necessarily an atmospheric chemist, but I do know ozone is very important to a lot of dynamics and climate and Earth systems. So it kind of leads you to believe that studying pulsating aurora and the energies would be really important. And with that, you can kind of combine this all together. So combining the fact that we know pulsating aurora are extremely common. When they do occur, they are very widespread over large regions of the aurora oval and can last for hours at a time. And combine that with the fact that these electrons are very energetic, sometimes almost an order of magnitude larger than your typical discrete or substorm aurora, and they can cause this ozone. You begin to build up this picture that we should really understand the energy of pulsating aurora at a very fundamental level and know how it varies on a statistical sense. Now, unfortunately, there are studies concerning the energy of pulsating aurora are fairly few and far between, and those looking at the statistics of the energy are even more rare. So now we can start to move to my research, because what we decided to do is try and fill this knowledge gap by conducting a statistical study of pulsating aurora energies using this device here, which is called the Poker Flat Incoherent Scatter Radar, which is this giant radio transmitter and emitter and receiver that's up near Fairbanks, Alaska. What this radar does is it fires pulses of radio waves into the atmosphere. Those radio waves then scatter off of electrons in that atmosphere, and from that backscattered signal, it can remotely sense a variety of parameters about the atmosphere. The one we're really interested in is the density of electrons in the atmosphere, because we know these incoming electrons are responsible for the aurora. So the density of electrons in the atmosphere is very important to and fundamentally connected to the aurora. This figure on the right is an example of some data that comes from this instrument. So on the x-axis, you have time over a couple hours. And the y-axis, you have altitude in kilometers. So looking at the upper atmosphere, it's radar basically looking straight up. And just to orient yourself, you see you have 100 kilometers here, which that's sort of the region that your typical aurora occurs around. And the color in this plot corresponds to that density of electrons in this region. Now, when you look at this plot, the first thing, and the thing that really stands out is this line that I've marked in dashed red, which is, you can see right at that line, you get the shifting of that electron density to lower altitudes. Now you're getting fairly significant density down here at 80, 75 kilometers. And if you remember back to what I said about pulsating aurora being caused by these more energetic, faster moving electrons, and that those faster moving electrons can penetrate further into the atmosphere, it shouldn't be too much of a surprise to hear that that red line corresponds to the start of pulsating aurora, as we measured with cameras or saw with cameras on the ground. Now we can actually take this electron density data and actually fairly accurately extract and model what the incoming energy of those particles that would cause this signature in the instrument to be. Now, the process for doing this is yes.
Riley, can I interrupt?
Yeah.
So can you go back for a second?
Absolutely.
What is the blue line there?
Oh, yeah. So this was taken from a figure. So yeah, the blue line just actually represents where these images were taken in this sequence of pulsating aurora.
Oh, I'm sorry. I meant the solid line going on.
Oh, yes. Yeah. So this solid blue line is essentially just a trace of what we would consider the lower boundary of this electron density. It represents anything greater than 10 to the 10th, a density of 10 to the 10th. In this figure. Yeah. Yeah.
Thank you.
Yeah. It's just sort of a lower boundary, kind of guide your eye in the plot.
Thank you.
Yeah. Yeah. So the process that we use to do this is fairly in depth. I'm going to skip over this for the sake of time in this talk, but if you're curious, definitely ask questions about this. And if you want to know more, you can read my thesis as well. There's a very detailed section on that. But I do want to show this plot here, because this is, for one particular instance in time, what our estimated energy flux was. So here in this plot on the y-axis, you have the number of particles, and then or the number of electrons, and the x-axis is the energy. So it's a measure of the number of particles at each individual energy. Now, I do want to touch on the energy units are in electron volts, which is just a common unit we use for measuring the energy of electrons. You don't need to know too much about it, but I do want to mention that kind of to get oriented, a typical energy range for discrete aurora would be between about 1,000 electron volts, so 1 keV, and maybe up to 10 keV. So kind of this region here. And pulsating aurora can actually be much more energetic. So this plot here shows the sort of distribution of energies that we have that would cause one particular data measurement from our radar. Now, our technique for getting this is fairly accurate if you look at kind of the broad sense of this spectrum here. But when you start getting into these smaller details, like these little bumps and spikes on this line, those are not as well defined for this process. And to mitigate the error in that for our analysis, instead of like trying to compare all these individual little bumps and spikes, we instead chose a threshold value, in this case 30 keV, and added up all the particles that had less energy than 30 keV and all the particles that had more energy than 30 keV to get then a low energy and high energy contribution to the total energy flux that's coming in here. We can then do this for every basically step in time for a whole bunch of different pulsating aurora events. And from that, get this large statistical data set that we can then start looking at to see how the energy of pulsating aurora varies compared to different metrics. And this figure here is sort of the key takeaway from that analysis in our study. So we'll go over it a little bit. So in this figure, what you're seeing is a series of these stacked bars. The height of the total stacked bar corresponds to the total energy. So here the y-axis is an energy flux. The height of the blue bar represents the contribution from energies that are greater than 30 keV, so that higher energy contribution. Well, the green is the lower energy contribution. Now this plot is split into two sort of subplots here. The one on the left is the first metric we looked at, which is how does the energy change depending on how long after one of these substorms, these bright auroral displays and kind of the crazy magnetic signatures, how long after one of those did we take our data? And what we see here is that close to the start of one of these substorms, between here 0 and 20 minutes after, we have the highest amount of energy that we're measuring. So pulsating aurora seems to be the most energetic close to the start of one of these substorms. And then as we get further in time away from the substorm, that energy gets less and less and the energy decreases. The figure on the right is another metric. This is AE index. And the way you construct AE index is you basically take a bunch of these magnetometers that measure Earth's magnetic field that are spread across the globe. You can then combine those measurements to produce this global index that gives you a sense of how strong one of these substorms is. So a higher value of AE index corresponds roughly to a stronger substorm. So here we can see on the far right that for these very strong, these strongest substorms, you again have the most energetic pulsating aurora and the most energy coming in. And the weaker that substorm gets, the less energy we have. So this figure here is really significant for the field of pulsating aurora and understanding the energy of pulsating aurora, because it really represents the first statistical evidence for how pulsating aurora energies vary in relation to these substorms, and shows a strong correlation with this energetic pulsating aurora and these substorms. And so we ended up publishing these results, and a big thanks to all my co-authors there in the Frontiers paper. But there was still something we were sort of interested in that last figure, and something we wanted to follow up on. And that's this figure here, the time after one of these substorm onsets. If you look close at this figure, you'll see that, yes, the total energy does decrease the further away from the substorms in time you get. But you'll also notice that most of that change seems to be from this blue bar, the higher energy contributions, where the green bar is changing less so. So it seems to be that most of this loss in energy is coming from those higher energy electrons. In fact, if we extend this out past 60 minutes and take the height of each of these blue bars, we can then plot those as scatter points on this plot on the right. So now you have energy flux on the y-axis and time after the substorm on the x-axis. So we plot those scatter points, and from those scatter points, we can then fit a best fit exponential decay to that. And from that best fit exponential, get a characteristic time scale to how these high energy pulsating auroral electrons are decaying after a substorm. And here we can see we get this time scale here of about 0.86 hours, so just under an hour. Now in physics, time scales can be really useful for tracking processes across different systems. So we were curious, could we use this time scale we're measuring here to track it across the pulsating aurora system? Could we use it to better understand where pulsating aurora themselves are coming from, which would be out here in the Van Allen radiation belt, the outer Van Allen radiation belt. So what we wanted to do is look for a similar time scale in a process that could change that mirror point, again, that point that the particle sort of reflects back on itself, and see if there was a process that would change that, cause it to be within Earth's atmosphere, that would decay with a similar time rate. Now, there are a few different possibilities for this, but the one that really stands out is something called chorus waves, which are electromagnetic waves that occur in the Van Allen radiation belt region, and specifically lower band chorus are what we're interested in. So chorus actually have two regions. There's an upper band chorus and a lower band chorus. And specifically that lower band chorus, we know it resonates with the same energy of electrons that we see and measure at the ground corresponding to pulsating aurora. So it seems like this might be a good candidate for that. And in fact, there have been some specific case studies and studies that have actually found and been able to measure a near one-to-one correlation between these modulations in the chorus waves out in the radiation belt and actual individual patches of the aurora. So the figure here on the right, so the figure on the top right shows basically the color just corresponds to the strength of these lower band chorus waves that the satellite measured out in the radiation belt. And you can see how these chorus waves are modulating and kind of pulsing on and off. And then the bottom plot there is a measure of the intensity from the camera on the ground of the pulsating aurora. And you can see how these modulations correspond very closely to those pulsating aurora modulations. So you have near one-to-one correlation with these lower band chorus waves and pulsating aurora. And then my advisor, she had a study from back in 2013 where she actually measured a near one-to-one correlation with, again, these pulsating aurora modulations on the ground with actual particles and electrons out in the radiation belt. And you can combine this together, you can pretty much say for fairly certain that in certain cases, this lower band chorus waves can cause pulsating aurora. But the problem is that these correlation studies are extremely difficult to do. And because of that, there have only been a handful of these that have looked at only a handful of events. So in a statistical sense, we can't really say how important are these lower band chorus waves to pulsating aurora. So we were wondering, could we use this timescale we had measured for this energetic pulsating aurora to have a better understanding of more statistically how important lower band chorus waves are for the formation of pulsating aurora. So we took this timescale we had there and did a big literature search to try and find if anyone else had seen a similar 1 hour timescale somewhere in the radiation belt. And we were able to find really just one paper, this Meredith et al. From back in 2000. And they actually found that these chorus waves, again, after a substorm, decayed here with a timescale just over an hour. So it seems very likely then that these two are somehow connected. We're having a very similar timescale with something we know can cause pulsating aurora and the pulsating aurora themselves. However, what you'll notice here in the figure on the right is that just due to sort of limitations in the data they had, there was only a handful of points they could use to get this decay rate and this time scale, maybe 20 to 30 of these data points, which, as far as statistics is concerned, isn't a huge statistical data set. So it's really hard to say for sure if that time scale holds up. We decided then to follow up on this Meredith et al. 2000 study and expand it to the newer and much more expansive Van Allen probes data set. Van Allen probes were a series of probes that flew for, I think, 7 or so years through the radiation belts and got lots of data. So we were able to expand that data set from 20 to 30 data points to here, kind of our distribution here of 224,000 data points. So a much larger, more expansive data set. And I have this figure here on the bottom, just as sort of an example of what these satellites are actually measuring. So what each of these sort of data points corresponds to. So this is the data, these wave data that these satellites would be measuring. The x-axis is time here, again over several hours, and the y-axis is the frequency of the waves. And then the color corresponds to the strength of that wave at the specific frequency. Now you see there are 3 different gray lines here. Those just basically mark the boundaries of the upper and lower band chorus. So lower band chorus occurs between this middle gray line and the bottom, while upper is between the top gray line and the middle one. And with this data, what we can then do is for each time step, integrate over these 2 frequency ranges. So integrate over the lower band chorus range and the upper band chorus range to get a wave power for the lower band and upper band chorus separately for each of these time periods. And then take that wave power and use that to see how this chorus waves are behaving after one of these substorms. So in this example here, this red line corresponds to the end of one of these substorms. And you can actually see how it, just visually, you can kind of tell how this wave sort of decays away and becomes weaker in time away from that substorm. So what we did is using this large statistical data sets and these individual wave power data from all of those points, we could then compare that and get a decay rate in these chorus waves after a substorm, which is what this figure here shows. But actually, in this case, had enough data that we could actually, in a large enough data set, that we could start subdividing even more. So in here, we've actually subdivided by what time of day that the measurement was taken. So the x-axis here is magnetic local time. Again, basically the same as local time, just measured off of the magnetic North Pole. And so this is, out here, this is more morning, daytime, have early morning here, and then nighttime. And the y-axis is actually the inverse of decay rate. And I do want to mention for my committee members, this is different from what is in my thesis. The last week or so, I was corresponding with some of the co-authors on this study, and we were changing some things based on that. So the y-axis is a inverse of decay rate. So in this case, a higher value is going to correspond to a faster decaying wave. When you look at this figure, one thing that's really interesting is here at this 3 to 6 time period, you see that the decay rate is much faster. These points are higher at that specific region. And what's really interesting about that is that also happens to be the most common time for pulsating aurora. So we should definitely look at that in a little bit more detail, which is what this plot here shows. So now on the x-axis, we have this time basically after the end of one of these substorms, over 3 hours here. And the y-axis is a measure of the strength, the power of that wave, of the waves. And here we've subdivided again, now by that lower band and upper band chorus. So lower band chorus is blue, upper band chorus orange. The scatter points are actual measured values for the wave power. And then the lines are the best fit decays to those individual upper and lower band chorus. And in this plot, you can clearly see that there is a difference between lower and upper band chorus, with the lower band chorus decaying here at 3/4 of an hour, a time scale, where the upper band chorus is nearly double that. So lower band chorus, which again, the lower band chorus are the ones that are associated with pulsating aurora, they're decaying at a faster rate. So this gets really interesting and cool when you start to compare this time scale with what we were measuring from our previous study down on the ground for energetic pulsating aurora. So again, remember back to this figure we had on the right, we measured a time scale of 0.86 hours for this energetic pulsating aurora on the ground. Now, if you can compare that to the time scale of lower band chorus, which we, again, in certain cases know can cause pulsating aurora, we see this very close sort of similarity between these time scales, where the lower band chorus is 0.75 hours, the pulsating aurora here, 0.86 hours. Now, a similarity in time scale is really strong evidence to show that these lower band chorus waves are important to the formation of this energetic pulsating aurora on more of a statistical sense instead of just in individual case studies. To add further sort of evidence to this, we actually simulated the system in a model. We worked with a team at UCLA to do this. And in this model, we basically input into the model all the decay rates we had measured for chorus waves at different times around, daytime, nighttime, morning. And then the output of that model was essentially the flux of electrons that would be precipitating into the atmosphere. And this plot here shows that. So the x-axis is time, simulation time, but you can sort of think of that as time after one of these substorms. And then the y-axis is a normalized flux of these electrons. And so in this plot, I've actually split it between more energetic electrons. The blue line here is greater than 30 keV electrons, and the green line is less than 30 keV electrons. So doing that to actually be able to compare back to this plot from that original study, where now actually the blue do correspond to each other and the green correspondingly as well. And so what we see in this plot on the right in our simulation is that the more energetic, this greater than 30 keV electrons, are decaying at a faster rate. You can see that line goes down faster than the green. So the higher energy decay in this model at a faster rate than the lower energy. And so that then is why we believe we were seeing this decay and this data we took from the ground, where most of this energy change is actually due to these higher energy electrons, just because they are actually decaying at a faster rate from up in the radiation belt, as this model shows. Now you can combine all of these together, so these two big studies. You start to build a picture of what a process that could cause this energetic pulsating aurora, which I've outlined here. So you start with one of these big substorm events. And in that substorm event, you get this injection of these energetic particles into the radiation belt region of Earth's magnetic field. That injection of particles can then drive and cause these chorus waves. And those chorus waves can then scatter and precipitate these energetic electrons in the radiation belt into Earth's atmosphere, where they then cause pulsating aurora. Yes?
I want to make sure I didn't miss something on the last slide, but am I wrong that your taus don't match?
Oh, yeah. I should mention that. I did want to mention that. So the timescales don't match here, but with the simulation, just some of the limitations of the simulation, we can't really cross-compare the actual timescales. I can go into that in more detail after this if you want to know. It's essentially the simulation is doing this averaging over all periods of time. But if we go back to this plot, we can see that we have this much larger spike at this 3 to 6 times. So if you sort of average over all the time, it's going to be a different time scale, just because it varies fairly significantly based on that local time.
Making sure I understand that answer, we should understand the time scale shown in the simulation as sort of a weighted integral across this plot.
Yes, sort of there. Yeah, it's like a little bit more complicated than that. And again, I'm not fully understanding the specifics of how they do the simulation, but it's called a drift average simulation is the way they describe it. So yeah, the timescales themselves aren't really cross-comparable between the two, but it's really the relative between the high and low energies that we're interested in. But the high energy does decay faster than that low energy.
So can I'll hold my question.
Okay. Yeah, so the last few studies we looked at were related to pulsating aurora. We kind of build up this picture of what can cause pulsating aurora. But I think as the field goes forward, we start to learn more about pulsating aurora, which is one of the most common and impactful types of this diffuse-like and dynamic aurora. It's going to be really important to start looking at some of the edge cases, some of the more unique observations that we've been seeing to really get an even deeper sense of how this type of aurora forms, which is what we did in our last study here. And so for this, we were actually looking at a particular interesting observation that this team here, Dave Knudsen, Tron Tronson, and Sarah Jones, made from back in 2002. And they had this really interesting observation, and it's not going to show up too well, but this is actually a picture of the notebook from that night that they made the observations. And the part I've blocked out here, they actually note that they were observed some pulsations that black out the diffuse glow, which then fills in again over several seconds. Now, if you study the aurora a lot, an observation like that is really intriguing. And you kind of wonder, what could be causing that, or we should look at it in a little more detail. Again, my advisor, Allison, she looked at this a bit in her thesis, but going into mine, we decided to expand on it more and try and publish some of these results, just to get this type of observation out into the field, so people could potentially do future studies on it. And so we coined the term the diffuse auroral eraser to describe this, what this observation was. And what one of these diffuse auroral erasers looks like is you start with this more diffuse kind of background glow of aurora. And then on top of that, you get this superimposed, brighter, more diffuse arc region of the aurora, we can kind of see here. And that lasts for a few seconds, and then it will suddenly disappear. And in its spot, that background of aurora, where the brighter spot had been, is now darker than it was before, almost as if someone had taken an eraser to it and scrubbed it away. And then that background will slowly recover and refill to its original brightness over 10 to 20 seconds. So we went through the 2 hours of data that this team had made, and actually found 32 of these such events in that 2 hours. So this is here what's known as a keogram. So on the x-axis, you actually have time. So I guess the way you make a keogram is you have a video, and in each frame of that video, you take a slice of pixels, in this case, down the middle of that frame. And then you stitch all of those slices together to produce an image like this. So the x-axis is time here, and then the y-axis corresponds to basically the pixel along that image frame, or the video frame. And in a keogram like this, these diffuse auroral erasers actually really stand out. They look like these brighter lines followed by this darker patch. So in this, we were able to find 32 of these. And then from these observations, basically use all 32 of those to construct what we consider to be kind of a typical or an average diffuse auroral eraser event, which this plot here shows. So now again, time you have on the x-axis, and y is just a normalized pixel value. So how bright the pixel was over this event. And you can see here that these eraser events start as this sort of background diffuse glow. You then get this brighter increase in that brightness, and then it suddenly drops off and becomes much more dim, and then slowly refills again over a course of 10 to 20 seconds. So we were able to produce these observations, and we ended up publishing this result in this paper here, again, thanks to the co-authors of that, to really get the word out about this observation. Now, unfortunately, because this was taken back in 2002, there wasn't a whole lot of other data we could use to try and piece together what exactly could be causing this type of auroral phenomenon. But it does seem to be like it's some sort of process where you have these multiple types of this diffuse and diffuse-like aurora, which are interacting with each other. You have that background, more just homogeneous diffuse aurora, and you have this brighter arc that goes on top of it, and somehow those two are interacting together. So it's our hope that by publishing this, it'll inspire future studies that will be able to find more of these cases and use those to better understand how this diffuse-like and dynamic aurora can occur. And so with that, I'll just sort of start concluding here. So throughout this presentation, we've seen that there are multiple types of this diffuse-like and dynamic aurora. So really interesting type of aurora that's definitely worth studying in more detail. We've seen that this type of aurora can be caused by these waves in Earth's magnetic field that can cause these particles to scatter and precipitate into the atmosphere. And for the case of pulsating aurora, we've seen that specifically lower band chorus waves can cause, lower band chorus waves in the radiation belt can cause that precipitation. And then for the case of pulsating aurora, we've seen that those electrons are extremely energetic and correspond with these substorms. And that those energetic electrons, when they hit the atmosphere, can have these very large impacts, such as the reduction of ozone, that can have significant, that can be significant to things like climate and space weather and a variety of other things. And so I'll kind of just leave you with this last thought, and that's the field of diffuse-like and dynamic aurora is incredibly impactful to the atmosphere, to the Earth and the near-Earth system. But it's also a field that is quite understudied. So I'm really excited to see in the coming years what future studies will be able to uncover about this very interesting type of aurora, the diffuse-like and dynamic aurora. With that, thank you.
Okay, let's do some public questions before we kick everyone out.
I have a couple questions. First of all, with the eraser events, how did you say you identify the events? Did you look through the eye, or did you have a
Yeah, so those were done by eye, and so I actually skipped over a little bit there. We did find 32 of them. It ended up being, I think, 23 or so that met what my criterion was. So this was just identified by eye in the videos themselves.
And then my other question, unrelated, is with in your first study you talked about where you split up the electron. First, like, how did you just test this out of very KB, and then did you test it on like the sensitivity of that threshold?
Yeah, so let's see, is this plot here? Yeah, so this these kind of thresholds here, yeah, so the 30 keV shows that it seems to often be, and depends a little bit on which paper you read. It's somewhere between often like 30 to 50 keV is that cutoff point. Just previous studies will look at less than and greater than that. So it sort of used it just to follow along with being comparable to previous studies. But yes, we did test the sensitivity of that threshold. So we looked at as well 50 keV, even up to 100 keV. And you correspondingly see a lower percentage of the, like at 100 keV, you're going to have much lower percentage of the total energy from that, but you do still get this similar decrease and similar time scale at those higher energies at 50. Yes.
So I think it was on slide 29, your plot with the electron efflux decaying. Or electron flux.
Oh,
Yeah, I was just curious. So it departs from like that exponential bit line. Is there like explanation for that?
Yeah, so this, I actually didn't mention it, but this is the best fit exponential to the first 30 minutes of the decay. And I should mention in these, when I'm actually fitting these to the first, I think it's hour, just over an hour on those decay rates. And it just has to do with, it seems like the dynamics in these systems, they don't, they'll decay for a bit along that exponential curve, but they actually tend to flatten out the further along you get, which we're not entirely sure what would cause that. There are a few possible reasons. It could just be that the total flux is kind of being depleted, and so you just can't, you have less of it, it sort of dies off and ends up getting sort of asymptotic into a background level, but there are other possibilities in that. Yeah, Jody.
Those diffuse surface events, do you only see them on that one day, or do they happen?
Yeah, as far as we can tell, these specific events are the only time this has been reported. There are similar reports. So for instance, it's known that pulsating aurora sometimes can actually, in the off phase of pulsating aurora, you can get a similar effect to this. But what's interesting is those are a much faster time scale and occur at this very like classic pulsating aurora, where these seem to be these individual events that just were like almost a single pulsation in a pulsating aurora. There's this couple cases where you can see it almost like repeats itself, but a lot of these are just single events. So as far as we know, this is the first real observation like this, or the only one. I'm sure there's almost certainly, I'd be surprised if there wasn't somewhere out there an observation, but just no one's been able to find it or report on it.
Yeah, but one thing that's been more popular these days is like amateur aurora chasers. And I'll say that this was the top downloaded paper I was mentioning earlier at the top of the talk. And so might be something like the Steve phenomenon, where we report on it once because we only have one real observation that we can find, and then amateur aurora chasers can come up with like a bunch of different events. We hope then we can use that to do different studies in the future.
Yeah, and actually the camera they used to observe this was a fairly, like I mentioned in scientific data, we often use these all sky cameras. But this was a very specific, much more narrow field of view camera that would actually maybe correspond a little closer to like the amateur